a material doesn't really have fixed plasticity, maybe I would. But instead, the plasticity model may actually have a use surface that are actually evolving. Okay, so what does that mean is that if I actually have a plasticity model that I initially have a use surface that looks like this, as I actually accumulate more dislocations or other plasticity behavior, the use surface may change into another shape. Okay, so talk about how to build the plasticity model in the last lecture. And this time we want to relax what we actually taking out in the last time. That is how to actually derive a more general plasticity model in which we have material that can undergoing hardening and softening, which translate to the revolutions of the yield surface. Not sure. This update. Okay, so I will actually show some derivation here. So consider your surface that are on the piping, and the piping can look something like this. No, it's okay. Okay. Now, when a material is actually undergoing deformations, in the small scale, there could be dislocations or other thing involved. And in the microscopic view, what actually happened is that if I consider a copper wire in a 1D loading and then I see the yielding, okay. So at this point, this is the initial yielding. Okay, and I start to accumulate plastic deformations. Okay, when I unload it, okay, I may actually encounter another yielding point here. Now this is the initial size of the yielding yield surface. Okay, so it tells you that from tension to compaction, this is how much the material yield. Now the interesting thing is what happened when I actually loading it for the second time. Okay, so there's a multiple possibility. First is that the material actually yield here. Okay, does that make sense? It can also yield a little bit earlier, or it can be a little bit later. Okay, we don't know. Okay, so why is that? Now let's look at it on the piping. In the perfect plasticity, the J2 von Mises yield criteria in this case would be fixed. In the case where the hardening or softening occur, then each time I reload the material, they may actually have a new yield surface. Okay. So that new yield surface, we actually don't know how it would look like. But for a common material, the first assumption that people often make is that it would be isotropic hardening. Okay, what is isotropic hardening is that it's actually very simple geometrically. If I have a circle here and then I consider the radius, okay, isotropic hardening basically indicating that the new radius is actually bigger than the original one, and I have a yield surface that are like this. Okay, it's become bigger, then that would be called a hardening. Okay, so if you represent it in the J2 plasticity, what you would have is that if I write the J2 plasticity as simply J2 minus Kuiper equal to 0. Okay, then what I would have, this is the perfect plasticity. then what I have in the hardening plasticity is the following. Plasticity, that are isotropic, I would simply write J2 minus Kuiper as a function of something. For example, plastic string would be equal to 0. Okay, so this one in the perfect plasticity case is a constant. It doesn't involve because the radius doesn't involve. Here the plasticity change with the, so here the radius of the U surface actually evolve with epsilon p. Okay, so what actually happened is that in this former case, this is perfect plasticity. The U surface is pinned down on the piping. In the hardening case, the U surface is evolving when I actually accumulate more plasticity. Okay. Now, this is actually the so-called isotropic hardening. Okay, so the work hardening meaning that Kuiper, the change of Kuiper, which is actually the radius of the U surface, is greater or equal to 0. Okay, or more strictly greater than 0. If we call it softening, softening simply meaning that the U surface is become smaller. Okay, you see what I mean? The reason is that in the hardening case, the elastic zone is actually expanding, and in the softening case, the elastic zone is actually shrinking in the stress space. Okay, so isotropic hardening is actually, we can see the literature from Roland Hills in 1950 from Cambridge. There are two famous types of isotropic hardening that are commonly observed in experiment. One is actually called work hardening. Another type is actually called string hardening. Okay. The difference is that in the work hardening case, we are assuming that if I actually introduce more plastic work, the hardening would actually change. Okay. The radius of the U surface is going to change. In the string hardening, the U surface radius is actually sensitive to the plastic multiplier. Okay, if you remember, the plastic multiplier kind of indicating the magnitude of the deformation, plastic deformations, without telling us the mode of the deformations. Okay, so but we haven't defined the plastic work. So what is this? So plastic work itself is actually coming from the dissipations, which actually have the sigma double dot epsilon dot p. Okay, so Cauchy stress, the scalar product between the Cauchy stress and the plastic strain weight. Now this one is not work. This is if you look at the unit, because of the time derivative is actually have the same unit as power. Okay. Now, but if you take the time derivative of it, that would indicate the plastic work that are actually done on the material. Okay, does that make sense? Okay, so I have that energy dissipator, I have that energy dissipation term that I integrated over time, then I actually get the plastic work term, WP. Now, for the J2 plasticity, this is actually specifically only for J2 plasticity only. the integrations is actually equal to stress. Let me put this to indicate this is a tensor. Double dot lambda dot s divided by the magnitude, of s times integrated over time. Okay, does that make sense? Now, this is actually something that will require the previous knowledge. If I make the previous, if I recall what we learned before, we would use partitions between the isotropic hardening and the directorial hardening to write the stress. This whole thing itself is equal to the Cauchy stress. Okay. Double dot S divided by S, the magnitude of the directorial stress times dot d tau. Okay, I'm just putting this term here. And that in return would be equals to what? Now, there's one thing very important. Pi double dot S is actually equal to 0, if you remember, because the dot product between something that doesn't have an isotropic component and P and S itself, they are orthogonal to each other. With that, then what we actually have is actually the directorial stress of S times lambda dot integrated over time. Does that make sense? Do you know why? So because what is the definition of this operator? This is actually equal to S double dot S 1/2, right? Do you remember? Okay, so S double S double S divided by S double dot S 1/2 is actually equals to S double dot S 1/2, which is itself equal to the norm again, right? Okay, so this is what we have. Now then, I hope that you will remember, or you would actually immediately seeing that what is lambda. Okay, lambda would be actually equals to, of course, lambda dot delta lambda, and that would be equals to lambda dot would be actually equals to the norm of the epsilon p dot. Okay, does that make sense? Now you need to understand that if I actually have a material that are yielding, lambda actually can change over time. Okay, can accumulate different plastic string over time. So and then you have this is actually a path dependent integrations. Okay, you see what I mean? So what I mean is that lambda dot actually is equals to the lambda partial derivative of lambda with respect to t, or you can actually argue that it's actually equals to delta n plus 1 minus delta lambda divided by delta t. Okay, but then the integrations would be a path dependent one, because t itself isn't that involve t itself is actually starting from the beginning to the current time that we try to integrate. You understand what I'm saying? It's a path integrations. So with that, we actually need to consider another criteria, which is actually the consistency of the plastic yield functions. Okay, so we're saying that one thing, if f is if the yield functions is actually, let me write, if the yield functions is actually greater than 0, then the stress, we're saying that the stress is not admissible. Okay, what does that mean is that this stress doesn't exist. Okay, it translates to English. You cannot physically make this stress, make the material experience this stress, because the material would yield, and then when the material yield, that stress is simply not possible. Okay. Then there another case where the sigma actually, when the yield function is actually equal to 0. In this case, the sigma itself become immiscible, but the material is yielding. Okay. Now remember that when we have an elastoplastic material, a material start to reaching the yielding point, and then they continue to yield, right? So this whole part, the material is yielding. Okay, does that make sense? Now, if I want to mathematically representing that the material is continuous yielding, so what we should do? In these whole regions, okay, from here to here, F is continuously having the combinations of the F, sigma, and Kuiper is continuously equal to 0. Does that make sense? Okay, because larger than 0 is impossible. Smaller than 0 means it's elastic. But I'm continuing loading the material, so it doesn't make sense that it's actually suddenly become elastic, right? Okay, unless you don't have convexity. Okay, you see what I mean? So what happened is that we also demand that F dot as functions of sigma and Kuiper also equal to 0. Does that make sense? Okay, because in this whole region, F supposed to be equal to 0. So that means F never change, right? If something is equal to a constant in the whole regions, that means it hasn't changed. If it changed, then it will sort of, then you have a way of change, right? If the curve is smooth. So F dot equal to 0 is called the consistency requirement. Okay? Now, for perfect positivity, what does that mean? Do you have consistency? We have consistency because Kuiper is not changing, right? Okay, so this whole thing is pinned on the piping, it doesn't move at all. So consistency is not that important for perfect positivity because by itself it should fulfilled, right? Now, for hardening positivity, which is actually a more realistic case of to model the real material, we would demand something else, okay? We were demanding that the change of the yield surface are consistent with the change of the stress in the following sense. Because F dot is equal to 0 and F is actually a function of sigma and Kuiper, the radius of the yield surface, and then the stress itself. So if I write it out in detail, what we will have is that the derivative of yield functions with respect to stress times the stress change way plus the partial derivative of F with respect to Kuiper. This is actually the yield function change times Kuiper dot is actually equal to 0. Okay, does that make sense? It's just a chain rule. Okay, can you see that? Okay, so what is the physical implication of that? Okay, that means there's a governing rule on how the yield surface change. Okay, so this seems very abstract, but I would say the following. What it actually means on the piping is that if I actually change my yield surface from here, from the green circle to the yellow circle, and by the way, because this is actually a homogeneous function, so the center of the yellow circle and the circle of the green circle, they share the same center. Okay, if you write a function for a circle, if you want to move the center, you have to you have to write x minus the center square plus the y minus the center position component square equals to 1, right? Or equals to the radius square, right? Okay, so they share. So what it actually means is that if I actually have a yield surface that if the material start yielding here, and I move from here to, if I move to this point, the yield surface need to grow accordingly so that it remain touching the arrow. Okay, do you understand what I'm saying? Okay, so this part is the change of the radius. This part is actually the stress arrow that are evolving in the stress path. Okay, you get what I'm saying? Okay, then we need to consider the two cases. Okay, so let's consider the first case. If we have a work hardening, then the Kuiper is the function of the passing work. Okay, so Kuiper dot would be equals to the partial derivative of the Kuiper with respect to the passing work times the change of the passing work. In this case, that would be equals to Kuiper partial derivative with respect to Kw times Wp times the strength, the rhetoric strength magnitude times the lambda dot, and that would be simply equals to Kuiper dot times Kuiper times lambda dot. Okay, do you see that? I'm just using a J2 plasticity that the magnitude of the rhetoric stress minus Kuiper equal to 0. Okay, so this basically, these two variables are exchangeable. Okay, because they equal to each other when the material yield. Now, if I consider the second case, which is actually the strength hardening, which, to be honest, I like it a little bit more, it's simpler. Then lambda dot is actually equals to Kuiper as a function of lambda times lambda dot. I think that's pretty obvious, right? Okay, just the partial derivative. Now, the interesting thing is that there are very specific names for this parameter, and this parameter. Okay, so sorry, these two terms. Okay, they are relating how does the radius change related to the change of the passing multiplier. Okay, and this term is called generalized passing modulus. Okay, so H is actually equals to Kuiper and partial derivative of Kuiper with respect to Wp, or Kuiper partial derivative of Kuiper with respect to lambda for the work hardening, and for the strength hardening. Okay, and H itself is actually the generalized passing modulus. Sometime. Okay. So in the most general form, these consistency equations can be evolved into this following constraint. The partial derivative of the yield function with respect to stress double dot stress change rate minus the passing modulus times lambda dot is actually equal to 0. Okay, so this is actually the general form that works for both the work hardening and also the strength hardening. Okay, so in practice, how does it work? Okay, how do we actually divide the hardening law? In practice, we actually need to determine what is these functions, okay, or what is these functions. Okay, and people have been using polynomial to do it, have been trying to curve fitting it with exponential component, have used symbolic regressions to obtain it. You can see a paper from Los Alamos a couple years back that using a symbolic regression to do it. Now, one thing that are very important is that this Kuiper is a 1D model. Can you all see that? Okay, lambda is scalar, and WP parsec work is scalar. It's a scalar map to another scalar that tell you the governing law of the radius of the unit surface. Okay, those can be determined from experiment. Okay, so you may ask how? How do we do it? Do we know how to do it? Do you know how we can actually find out exactly what is this equation? Okay, the most simple case to do it and have been used a lot in metal but not so much on geomaterial is the following. We would consider using a uniaxial test. What is a uniaxial test? Is like putting a couple wire. There's two ends and apply loading to it. Okay, and that loading is sigma. Sigma is not the tensor, but simply the applied normal stress. If I actually recall what we learned before, then we just stress tensor in this case is sigma 0, 0, 0, 0, 0, 0, 0, 0 here. Okay, only one unknown. And as a result, the reverse stress is 2/3 of sigma, 1 minus 3 sigma, and 1 minus 3 sigma in the diagonal term. Okay, so far so good. And the magnitude of the stress is actually equals to 2 divided by 3 square root sigma y, which is actually equal to Kuiper. And if you recall from the previous lecture, the square root of 2 divided by 3, sorry, I think previously I say 2 divided by 4, that's not correct. 2 divided by 3 square root is actually called the distortion factor. Okay. Now we can do the same thing by actually calculating the parsec strain. Okay, the parsec strain rate actually should look like the following. That should be the axial epsilon A is actually the axial strain, and that should be equal to 1/2 epsilon A P dot, 1 epsilon 1/2 P dot. Okay, without any new information, I would know that why do I have the minus 1/2 and minus 1/2 in the other two components? Huh? Yeah, actually, that's very good. Isochoric. Okay, why is it isochoric? Yeah, actually, right. Okay, then why is trace equal to 0? Yeah, exactly. Because it's J2 parseticity, you're not supposed to have parsec volumetric deformation, right? If there is no parsec volumetric deformations and then deal with a cylindrical coordinate, right? Then it makes sense that these two coordinates would actually have the same type of parsec deformations in the radial direction, because both of them are radial direction component, right? It doesn't make sense for one to have more, right? Now, but then I also have the trace of the epsilon. I also have the trace of the epsilon dot p has to be equal to 0, okay? So the only way to actually make this constraint fit and this symmetry fit is to split that total amount in half, right? Okay, because the epsilon epsilon dot p 22 and epsilon dot p 33 should be identical. then it's split by half, and then I add the divergence, I add the diagonal component together, I get nothing. Okay, so that fulfill my goal of having no passing volumetric deformations. Okay, now go back to the business. Then if I take the calculating a norm, I would simply have lambda dot. Okay, by definitions. Now, then what actually happened is that if I actually have in this case, then the U surface is supposed to changing in the way of equals to the hardening modulus times the epsilon A dot P. Okay. And so, but epsilon dot AP is actually is actually equals to, according to what we did before with the distortion factor, is 2 divided by 3 lambda dot. And the change of the U surface, the way of change of the U surface, according to what we talk about, is actually equals to the reverse of the distortion factor times Kuiper dot, according to what we talked about in the previous lecture. Now with the two things combined, then I simply have lambda Kuiper dot equals to 2 divided by 3 h pi lambda dot. Okay, so I think you all see the interesting pattern now. So at the end, the hardening modulus is equals to the partial derivative of f with respect to Kuiper times the passing modulus, which is actually simply 2 divided by 3 h pi. Okay, so you have the material yielding. So what happened is that if I plot the passing strain rate change in the axial direction where the material is low, I would actually observe this ratio and this from the initial yielding, and this would give us the hardening modulus. If I actually looking at it from the passing strain of passing multiplier point of view, then I have the Kuiper, and initially the U surface have this radius, and it will grow in 2 divided by 3 times h pi. Or actually, sorry, I need to write it more carefully. Yes. Anyway, so that would be the way to determine the hardening. Now, there's another completely different plasticity. What we show is isotropic hardening. In metal, you rarely have isotropic hardening. The reason is the following. If you yield the material in the tension directions, usually the compassive directions are actually getting easier to yield. Okay? On the other hand, if you're loading it, if the material is initially yield in the compassive directions and then you're loading it in the opposite tension direction, then the tensions turn to a curve earlier. So that lead to a completely different not completely different. It lead to a different mechanism where I have. Okay, so what happened? What happened is that we would actually write the U surface now as a functions of the derivative stress minus the back stress minus Kuiper equal to 0. Okay? Can you see what is the geometrical meaning of that? That actually, what it means is that on the piping, actually I should write it in this consistent order. Sigma 3 is at the top. Sigma 2 here, sigma 1 here. Okay. My initial U surface could be a circle like this. My new U surface is actually here. However, the radius, Kuiper, and this Kuiper, so are actually identical. Okay, so Kuiper equals to Kuiper in both cases. Okay, does that make sense? Okay, what it actually shows is the following. If I actually loading the material, let's say I consider a 1D case. If I loading the material in pure sigma 1 directions, okay, then the material would start to yield here. And then instead of making the yield surface larger to follow to compensate for this arrow become bigger and bigger and bigger, I will simply keep the same yield surface and then moving that yield surface so that the tip is actually on the one part of the yield surface. Okay, does that make sense? Okay, you can think about isotropic hardening, sort of like a balloon. I can push more air to make the yield surface bigger and bigger so that the tip of the arrow is just touching the boundary of the balloon. Okay, does that make sense? And then the kinematic hardening is like a rigid ring on the piping where the ring is, the radius is fixed, but as I pushing the boundary, then the yield surface keep moving. Okay, so that geometrical interpretations can help you think about how to implement. So actually what happened is that the back stress and the rotary stress in J2 facility share a very important property, and that is the chase of the back stress is actually equal to the chase of the directory stress, and they are both equal to 0 by definitions. Okay, why do we want to have the back stress to be to have a trace equal to 0? What if it's not equal to 0? Now, considering that in the piping, you actually consider a special case of this. Okay, you see what I mean? Now, this line is the P sigma 1 equal to sigma 2 equal to sigma 3 line. Okay, so if your back stress is actually not, if your back stress, the chase of the back stress is not equal to 0, then what happened? Then if you want to keep the 1 meters, it start to have rotation, right? Okay, so here you will still move. Okay, there will be a transitions, but there is no rotations on the piping. In fact, if you draw a flat surface here or here or here, then the kinematic is restricted to moving in that projections on that plane that are orthogonal to the hydrostatic axis. Does that make sense? Okay. If the back stress is the chase of is not equal to 0, then you kind of have to have it tilted in the sigma 1 equal to in the along the hydrostatic axis. Okay. Now then, what actually happened, as you can imagine, is that the kinematic hardening has a completely different consistency criteria. The consistency also require F dot equal to 0 because you want the stress to remain at the yielding surface. However, that will lead to a different consequence here. F is actually now equals to this, and for simplicity, I would simply say that I would use this label to represent the directory stress minor alpha, and F dot. If I actually work on the chain rule, that would be equals to 1/2 of the difference between the directory stress and the back stress times to 1/2 times 2 of this scalar product plus the additional term Kuiper. But because since Kuiper is actually a constant, then Kuiper dot is actually naturally 0. So this thing cancel out, and this is equal to 0. And what happened is that, so this one would be the recenter directoric directions times the S dot minus lambda dot is actually equal to 0. And interestingly, this one would be the new passing flow directions if the passing flow is associated. So now let me look into the details of the consistency functions. No, I don't. Oh yeah, I missed this dot here. I think I know what is the problem now. Okay, this is just I think this is just the product rules here. Okay, from calculus. Now let's take this. Let's write out this term. This would be equals to the partial derivative of the directoric backstress difference times the partial derivative of it with respect to stress, and that would actually be equal to this. Okay, this term is 0 because the back stress is not a function of the cosine stress. They're independent. Okay, so this part is automatically taken out. This part, if we recall from what we did before, we did make the derivation before, and if this one is actually the passing flow directions, then what we have is that this whole term, the stress gradient, is equal to n double dot I, the fourth order tensor, identity tensor times the 1/3 of the second order identity tensor times the I itself, and this is a fourth order tensor. And one important property of this matrix is that this is simply equals to, if the dot product between this fourth order tensor and n, the second order tensor, this fourth order tensor and this second order tensor is simply n itself. So we come up with this. Okay, so the important conclusion we have is that the passing flow directions, so the stress gradient is actually equal to the stress gradient with respect to the renormalizing stress that are actually corrected by the back stress. Okay, so now finally, if we are actually using the notations of this as n, then the consistency requirement would simply require n double dot s dot minus n dot lambda dot equal to 0, and that would actually simply lead to the directoric stress times lambda dot minus n double dot gamma dot equal to 0. Okay, so in principle, what actually happened is that you have a rigid body translations in the piping. Okay, does that make sense? Because the amount of the stress change is more or less equal to the change of the back stress. Okay, so you only grow the back stress when the stress is changing in the same along the same directions where the yield surface is changing. You can essentially thinking about, you have a rigid ring, and then your stress is actually a tip. It's like a finger that moving this yield surface. Okay, the yield surface doesn't change the shape. Okay, it's just the center that keep being changed. Okay, and there is a specific name for it. It's actually named after Prager, which is actually one of the mechanicians in the after the World War II. There's a metal name after him, the Prague's metal, and this is actually what we call the Prague's translation rule, and that is that is actually equals to the hardening modulus times epsilon dot p, and that would be equals to h lambda dot h lambda dot times the stress gradient, which is actually equal to h lambda dot n. N is actually the passing flow directions. So this looks really abstract, but what it means is that lambda, the back stress, move along the directions of epsilon dot p. Okay, so, and this is actually the change of the stress in the stress gradient term times dot minus h lambda dot equal to 0, which is actually identical for the between the isotropic hardening and the kinematic hardening. Okay, so far so good. Okay, so now what happened? Imagine that you have a wing that are expandable, okay? Or imagine that you have a wing that are made with a balloon or whatever, okay? So in real life, you don't see the pure kinematic hardening that often, and you also don't see the pure isotropic hardening that often. So what should we do? We would actually have to write a positivity model that both change the size and also change the positions, okay, the position of the center. So if we combine the two things together, which is actually often time what we actually require, we get a combined isotropic kinematic hardening. Which we will talk about the implementation in the next lecture. Now let me recap what we have. If we have an isotropic hardening, the U surface would actually change its size, but not the center. So what it shows is that the back stress equal to 0, or you can the change of the back stress equal to 0, or you can simply say that there is no such thing as a back stress for isotropic hardening. Then we have kinematic hardening, and that would be Kuiper dot equal to 0. The size of the U surface doesn't change. However, the center of the passing string is actually changing along the directions of the passing flow directions. Okay. Now, I think I used the wrong color, but I think if you understand what I'm talking about, then we have the combined hardening. Okay, then I have the Kuiper that could change. And I have the center of it that can also change. Okay, so beta is actually is within the range of 0 and 1, okay? If beta is equal to 0, obviously what you get is purely kinematic hardening. If beta is equal to 1, you get the purely isotropic hardening. Okay? Does that make sense? Now, the question I want to ask you is that why is it between 0 and 1? Why is it not 0 and 5? Or 1000? Why is there an upper limit and a lower limit? Okay, think about it on the piping. Okay, initially I have that U surface, and then I'm actually touching it, right? Now I lower it even further, right? okay, and I want the U surface to touching, I want the new U surface to actually touching it, okay? You see what I mean? And I have two machinery for me to move the U surface or change the U surface in a proper way so that you just touch it. Okay, I'm allowed to moving it or expand it, but not doing any other thing, not changing it into ellipsoidal or any other thing, right? Okay, so if I move a lot of that U surface, if I move the center a lot, then I cannot expand that much, right? Okay, if I expand a lot, on the other hand, I cannot move that much, right? And what is that relation? What is the budget I have? The budget is the difference from here to here. Okay, in between this part, okay, I can choose to expand or I can choose to move the center, but that total budget is actually related to what is this term? It's actually simply related to this, right? This is actually the amount of the stress strain along with the directions of the stress gradient, right? Okay, so once I'm using up this budget, I cannot change the U surface any further. Okay, and that total budget is actually allowed these two different modes in a combined isotropic kinematic hardening. Okay. Okay, so why don't we take a break for 15 minutes, and then I would complete the implementation algorithm of the combined isotropic kinematic hardening, and after that we go back to the neural network part. Okay, we'll talk about how to actually introduce neural network without explicitly doing the kinematic and isotropic hardening. Just consider it as a generic problem where the U surface is actually evolved. Okay. Okay, let's take a 15. Let's come back at 5:30. Is that okay? I just cut 1 minute from the break. Okay, so let us continue. I would like to finish the algorithm part first before we talking about the level set positivity that are generalizing this concept of evolving U surface. Okay. So this part we would like to discuss is the computer algorithm. So before, what happened to the color? Before we are talking about the theory of the J2 positivity and then provide a geometric interpretations of the J2 positivity with a combined isotropic kinematic hardening. Now we not need to talk about how to put this in computer. Okay, in computer again, we don't have the luxury to consider continuous workflow, but we can discretizing it. The basic ingredient between hardening and positivity and perfect positivity are very similar, except that we need to consider the hardening law, which previously doesn't exist. Okay. So here in this particular case, I will consider a linear hardening law in which the passing modulus and the hardening modulus are both a constant that doesn't evolve with time. Okay, so the first criteria we need to consider is that I'm assuming that the change of the stress is only depends on the change of the elastic strain. And there is a partitions between the elastic strain and the plastic strain that form the total plastic strain. And that will lead to these equations. I hope by now you're familiar with it. And if we use a retard mapping algorithm, that would give us sigma n plus 1 equals to the trial stress minus the correction term, which is actually this last term is equals to 2 times the shear modulus times the delta lambda times the n plastic flow directions at n plus 1. Okay. using the backward difference. Then there's a new rules here that are new, and that would be the hardening rule number 1. Again, hardening rule is actually the rules of how the U surface evolve in the light of the plastic deformations. Okay, let me say it again. A hardening rule is actually what govern the U surface evolve against some kind of plastic deformations. Okay, you see what I mean? And we have 2 hardening rules here, and they need to evolve with rules that are actually defined. The first one is the isotropic hardening rule, which is actually Kuiper dot equals to beta h lambda dot. Okay, if I assume a linear hardening, h is actually simply a constant. And in the discretized form that are ready to put into a computer, I was just saying that the new hardening, the new radius is actually equals to the old radius plus the change that happen when I accumulate plastic when the plastic multiplier change from step n to step n plus 1. Okay, so far so good. This is pretty obvious. Now then there's another hardening rule number 2, that are related to the change of the back stress. The back stress is actually changed in the amount of 1 minus beta h lambda dot n. Okay, there's a big difference here. I want to emphasize again. Kuiper is a scalar. Okay, the back stress on the other hand is always a second order tensor. Okay, you see that? It has, so sigma, sorry, not sigma, alpha always have the same kind of expression as the stress itself. Does that make sense? Or more rigorously, I would say that alpha has the same rank as the Cauchy stress, and also the same property in the sense that alpha must also be symmetric. Okay, why is alpha need to be symmetric tensor? Because Cauchy stress is symmetric. Okay, and it operates in the stress space. Okay, so that will lead to alpha n plus 1, the new back stress equal to the previous old stress plus the change that are actually allowed by the hardening mechanism. 1 minus beta h delta lambda n plus 1. Okay, now one thing that are very important for J2 plasticity, or in that sense passive insensitive plasticity, is that the chase of n plus 1 and the chase of the n plus 1 child stress are actually equal to each other. Okay, you see what I mean? And the directoric stress is actually equal to the tri-directoric stress minus the correction term. Versus, if you recall from the last lecture, the mean pressure and the actual mean pressure are identical always. Okay? Is it true? Is it true? Yes. I just want to put a little bit of pressure. Okay. Is it? Again. Let me say it again. The tri-directoric stress and the tri-directoric stress and the two-directoric stress are always separated by the corrections, because there's a J2 plasticity is sensitive to the directoric stress. Okay, but the mean pressure should contribute only with elasticity, right? Okay, under the assumption that the elasticity is isotropic. Okay, if it's anisotropic, then what happens? if it's an isotropic, then you apply the volumetric strain to it, it would develop volumetric stress and vice versa. Okay, so that need to be think more carefully. Depends on the particular directions of the plastic flow, you can get different response. Now go back to this. Okay, so we are in the directory stress. Now, then what actually happened is that I also need to consider the distance, the difference between the directory stress and the back stress. Okay, so can this thing become bigger or smaller? It could, right? Because I have a combined kinematic hardening, so the distance or the difference between them are actually keep evolving. So if I substitute what I have here, then I will have this term. I basically just substitute the whole thing that we talk about here. And that will lead to, if I put these two terms together, then I will have the tri-stress of the S minor lambda, S minor alpha, and then the second term would be equals to 2 lambda, 2 times the shear modulus times delta lambda plus 1 minor beta h delta lambda, and this divided by the magnitude of the difference. Okay. So recalling that, if I actually calculating the norm, then I will have this norm of the directoric and backstress difference equals to the tries of it minus 2 delta lambda minus 1 minor beta h delta lambda. Okay, does that make sense? Because I simply apply the whole thing with the measure. So here and this term. Okay, can you see that? And so what happened is that, because that would simply equals to Kuiper n plus 1 and equals to Kuiper n plus beta h delta lambda. If I actually see that from the radius point, so delta lambda is actually equals to the chase of n plus 1 minus k Kuiper n divided by 2 shear modulus, 2 times shear modulus plus the hardening modulus. So I can simply, if h is actually constant, I can simply update delta lambda. Okay, so far so good. Now then the next thing is that I also need to update the constitutive tangent operator. Okay, why do I need to introduce the tangent operator? Okay, in your finite element, okay, what is your strength? What is your strength? Your strength comes from the infinite element. Your strength comes from the B matrix times U, right? Maybe I'll put it as a box. Okay. Is there such thing as an elastic displacement? Okay, I don't know how to define it because deformation is not depends on displacement at all. It depends on the relative displacement, right? Okay. When you put it into the finite element, what you need to obtain is the tangents, and that tangents need to be computed. And for simplicity, I will assume isotropic elasticity. Isotropic elasticity lead to the following expressions. CE, the elastic tensor, is actually equals to the Buck modulus times the the tensor product of two identity matrix plus 2 lambda times the fourth order identity matrix minus the tensor product of the identity matrix. And so sigma dot equal to CE double dot epsilon dot minus lambda dot n. Okay, now, but here we want to do something different. What we actually want is to as CEP elastoplastic tensor double dot epsilon dot. Okay, so I want to somehow re-expressing this and this such that I can actually write something like this. Okay, so this is actually related to the tangents. So in a stress strain curve in 1D, okay, so I can have a nonlinear relationship between stress and strain. The ratio, the slope between the stress and strain are here. Okay, from 0 all the way to this point. Okay, but the tangent is actually this one. And they keep evolving. One thing that are not explicitly written but are very important is that the tangents is only well defined at a given point. Okay, if I say that this is actually a tangent without telling you with respect to which point in the stress strain curve, I did not provide you any information. Although you can argue that the revolution of the CEP can be derived into a general expressions. Okay. Now I want to go back to that. The derivation of CEP is very important because in the finite element, this is actually what you put into the computer in the global Newton-Raphson algorithm. Or at least you need to put the algorithmic version of it. So the consistency in this case will require F dot equal to the stress gradient double dot sigma dot minus h lambda dot equal to 0, like what we talked about before. If I actually do the derivations, then what I would have, we expressing this sigma dot in terms of using the root 1, where the stress change is actually related to the tangents of the elasticity times the difference between the elastic and plastic strain, then what I would have is actually this. Okay, now what I actually could do is that I can put every term here on one side and then do some algebra, and I will have lambda dot equals to n double dot CE double dot epsilon dot divided by n double dot CE double dot n plus h. Okay, or I can write it in the tensor form, in this case n ij c I j k l epsilon dot kl divided by n I j c e I j k l n k l plus h. Okay, this is a scalar divided by the scalar. And as usual, we want this thing to be, if we call this thing x, then we want x to be greater than 0. Okay, you see what I mean? So what is the physical implication to that? If this is greater than 0, that is, h could be negative, but it could not be more negative than the first term. Does that make sense? Okay. If it's more than this, then what will happen? If this become negative, then what happens? I just want to challenge you to connect the mathematics to the physical world so you know what you're doing. So with this term, if your H is actually so horribly negative, super negative, okay, then the whole thing could become negative. And what will happen? Why is it terrible? Yeah, then your positive multiplier become negative. So what does that mean? Your positive multiplier is monotonically increasing for given reasons. You can develop more plasticity, but if you actually dissipate more work, you cannot make the material more elastic, okay? You see what I mean? So what if it's negative, what it means is the following. The string, this thing go into the one directions and I develop the plastic string in the opposite directions, which is actually equivalent to saying that I make the thing more elastic, okay? So that makes no sense, okay? Now go back to this. If I actually writing it, if I want to further write it in details than what we will have, just for simplicity, I want to talk about a different topic. Is that CEP would be equal to CE minus 1 divided by the x that we defined before times CE double dot n times n double dot CE. Okay, so for perfect plasticity, for what we talked about before in the previous lecture, if the plasticity is perfect, which means that the U surface doesn't involve, then x equal to 0, x actually equals to n double dot CE double dot n. And in this case, what happened is that, what would happen? If you actually remember what we talked about in the last lecture, CEP is not necessarily have 0 component, but in perfect plasticity, CEP is singular. Okay, what does it mean by singular? Singular meaning that you have at least one eigenvalue equal to 0. Okay, this is actually why the perfect plasticity, that's one interesting thing, is that it's simultaneously the easiest one to derive, but then the hardest one to integrate, in particularly reloading in the plastic directions. You may easily lose the stability simply because you are meet multiple solutions. Okay, so this is actually what happened in an actual computer algorithm. I have the elasticity. In this case, I actually first compute the partitions of the, assuming that all the elastic string are actually elastic. Okay, I may actually decomposing it with the eigenvalue and the eigenvector, or we don't have to do that if you don't want to do it in principal stress. We update the stress. We actually compute check whether the material is actually yielding, and then if it's actually elastic, then the charge stress and the actual stress are equal to each other. Okay, if it's not, then this is actually the major dish of the plasticity. Okay, you see what I mean? This is actually the part that we need to talk about the detail, and then maybe we need to solve it in Newton-Raphson. Is that I need to actually find out what happened to the plasticity. Okay, so what do I mean is that I need to find the stress. Okay, because the stress update algorithm. Or equivalently, I can say that I need to find out what is the elastic string, which is actually the same way as saying that I want to find the stress. Do you see why? Okay, because in each step, the new string is actually given. I just simply need to partition it into elastic part or plastic part. Then I can actually already update the stress, right? You see what I mean? Okay, or equivalently, I can say that I want to know how the stress change, and then how does the plastic, how does the hardening things evolve, and I can solve the problem. And I put all the constraint there, and then I can get the update. Okay, now in a more general sense, what we talk about is a particular yield surface, but in the most generic sense, the plasticity, you can think about any plasticity surface as just some kind of functions of stress that evolve in some internal variable. Okay, so, and we don't know what it is, but we can maybe put the name something like this here. Okay, and in this particular case, we simply don't need to assuming that the elasticity is actually evolved in any particular way. It doesn't need to be kinematic, it doesn't need to be isotropic, it just need to be changed, right? Okay, so does that make sense? Okay, because if I changing it, I actually evolving the yield stress, and I know that is not a perfect plasticity, right? Okay, so isotropic hardening, kinematic hardening, they're just two ad hoc examples that we add so that we can finish the model easier. Okay, but in a more generic sense, it's just a level, it's just some kind of function that they evolve over time, right? Does that make sense? So in fact, there are non-theory to do that, and that would be the implicit representation theory for interface. Okay, you can represent an interface by actually putting a equation like this. Okay, so we don't actually want to necessarily write the interface, but we say f equal to 0 is actually the interface. Okay, and that actually is provides a simple way to represent a boundary. Okay, so let's consider the circle as one example. Okay, how do I mathematically write a circle? Okay, how many of you know how to write the equation for circle? Okay, how do I write it? There are at least two ways. Okay, what is the first way to write it? Okay, that's excellent. What is the second way?
R is equal to
R
is equal to big
R is equal to big R. Yeah, you can. Okay, this is actually changing the coordinate. But I'm saying that if I don't want to represent it implicitly, okay, I want to create a yield surface, the boundary. Okay, so this is actually, so this by the way, this is not a circle. If I write f equals to x squared plus y squared minus r squared, minus r squared by itself is a scalar function. It's not a circle, right? Why do we see a circle here? We have to add an additional term f equal to 0. Okay, at f equal to 0, or maybe f equals to 1 or whatever, then you can see a circle, right? Do you see that? Okay, so because this function is well defined, it's like a color contour here. Each of the contour give you a circle. You have infinite amount of the circle here. If I actually write along f with a constant number, right? Okay, you see what I mean? Do you understand what I'm saying? When f equal to 0, then you have a subset of these two Euclidean vector space of dimensional 2 of the function where you're drawing or you're on the circle, right? What is the other way? The other way is very simple. We just say sine t and cosine t. Does that make sense? And t is actually belong to 0 and 2 pi. Okay, you see what I mean? Then along the t, I would actually create a parametric curve to actually create a circle. Okay, so which way is better? What is the difference between the two cases? They're not identical. So in here, t, if you actually think about t as some kind of time, it actually, you actually not only do you get a circle, you start to drawing it, right? Okay, from t to 0, you actually give you a sense of direction, not just this. As t is evolved, you actually evolving it. Versus here, you don't have the sense of directions. Okay, so anyway, so anything that can be defined as a criteria can be defined in an implicit way using scalar functions in a higher dimensions, or directly as a parametric curve or parametric hypersurface or whatever. Okay, you can parameterizing it or implicitly represent it. So yield surface in a classical way is actually represent implicitly. Okay, and then the way to evolving it is also completely different. So how do you want to, if you want to imagine that you're interested in writing a 1 meters in a parametric curve and have sine t and cosine t, and now I want to make it bigger, so what should I do? How do I make it bigger? Oh, I can put a constant here, right? I will also maybe, I don't know, maybe put a chi here or whatever. You can make it bigger, right? But you see the representation affect the governing of the how to representing it. Okay, if I want to moving that parametric curve, is sine t and cosine t, what should I do? Yeah, I can deal with the t, I can be parameterizing it, right? I can also move this thing, or I add a constant. Okay, but then they are actually just necessary to be evolved in the same way. Now here, let's talk about just the J2 positivity is actually just a yield function that looks like this. I think I would